Hello everybody, this is Dr. Dave with Physics 152 at K College. I want to talk to everyone today about wave interference. Hopefully you had an enjoyable and restful doggo yesterday, and let's try to work together to get to the end of the term now. So, we need to first start by talking about wave superposition. We have been doing superposition all along. When we had two different vectors, we would add them together, and now we're adding up a collection of vectors. So there's a vector that, each one of these waves is representing a vector pointing from this zero line up to that point there. So in this first example here, I'm adding waves together, and so my peaks are going to get even taller, and my troughs are going to get even deeper. However, when I add 0 to 0, I'm still going to get 0. So that's what we see. We see here that the two peaks got really tall and the two troughs got really deep, but what was 0 stayed 0. Well, what about when we're not in a simple overlap like that where everything is behaving friendly? Well, now in this case, when I add these waves together, I'm going to add this height from the red wave and this height from the blue wave, and I'm going to get my peak somewhere around there. And then when I add this depth from the red and this depth from the blue, I'm going to get my peak somewhere down there. So this is what that superposition looks like, whereas this height can be found by adding these two individual pieces together. So what we see here is that the overall amplitude of this superposition at the top is the largest compared to this one. That is, if the two waves are not perfectly lined up with one another, when you add them together, while in this case you're still getting a wave that's taller than either the blue or the red wave, you're not getting a wave that's as tall as it could have been. Let's look at the next case. So now here I have further shifted my waves so that they're not overlapping peak to peak, but they're not overlapping peak to trough yet either. They're doing something in the middle. So my peak is still going to occur around right here where I'm adding these pieces together, and we get something that looks like the following. So now I've taken two waves and I've added them together, and I've created a wave with a smaller amplitude than either of the original ones. So let's keep going with this example. So now I have two waves that I'm going to add together, but they're really far offset from one another, so that when I add them together, I've now diminished both of these waves and created an even smaller wave. Well, what happens in this final case? Right, in this final case we look at, everywhere the red wave is a peak, the blue wave is a trough, right? And vice versa, everywhere the blue wave is a peak and the red wave is a trough. When I add those together, I get 0 everywhere, right? So there's nothing happening there. So what's waving? What's waving here, if it's water, is the surface of the water, right? If it's light, then it turns out there's electric and magnetic fields that are waving. If we ask really what is this wave representing in terms of electric fields or even displacement vectors, this is telling me the amplitude of, say, my electric field. So these could be electric field vectors that are telling me the electric field at this point in space, when the wave travels by, goes upwards by that amount. Now light, which is sort of the focus of what we're doing right now, turns out to be an electromagnetic wave. What does that mean? Well, it turns out there's an electric wave that is perpendicular to the magnetic wave, and the electric field is oscillating up and down in, say, the XZ plane. And the magnetic field is oscillating back and forth here in the YZ plane. And then the wave itself is traveling to the right. Now, we don't need to get into those details. All we want to really be thinking about is that we learned that a changing magnetic field, which is what I get here, right? A changing magnetic field over time is going to create a changing electric field over time. Now, what we didn't get into in this course, but is also true, is that a changing electric field also creates a magnetic field. So this is what we call a self-propagating wave. As the electric field oscillates up and down, it creates a magnetic field that, as it oscillates up and down, creates an electric field. Now, all of that is details that we don't need for today. What do we need for today? What we need for today is just to remember that when I'm thinking about a wave, I'm thinking about something going up and down. I'm thinking about either displacement up and down, or electric field up and down, or even magnetic field up and down. That's what I'm thinking about. So one important thing is our eyes don't detect peaks or troughs. That means that my eye can't tell if this part of the wave is getting to me or that part of the wave is getting to me. It doesn't know. My eyes just know, did light arrive or did no light arrive. So if I was standing right here observing, I would not see any light. All right. So now we want to think about a circular wavefront. And what do I mean here? Well, what I mean now is that I have a source of light, and this source of light, let's just imagine your foot dangling over a dock into a pond, and your toes tap, tap, tap. And as your toe taps, it sends out these ripples, and these ripples, and these ripples, and these ripples. And as those ripples go out, they leave behind a wake. And these are the wakes traveling out. So this is what we call a circular wavefront. It's traveling in each direction. Okay. And we have peaks and we have troughs. So to help us understand that, let's take a slice down the center. So if I slice down the middle here and I say, what is this wave doing? Well, here the wave is a peak, and here the wave is a trough, right? So this is the top, that's a bottom, that's a top, that's a bottom. And I could draw this sinusoidal wave. It would be a little bit hard to see from this vantage point because it's just up and down in the plane. So I'm going to instead turn it on its side. And I'm going to then extract it out here. So what do I mean by this? Well, these are my peaks, meaning these are my blues, and these are my troughs, meaning these are my reds. So you can see this lines up. All of my peaks line up here. And all of my troughs line up there. So in any spot along here, I could just take a slice. And that slice would look just like it does over here. So when you see this wave pattern that we're looking at right now, that is just peaks and troughs spreading, you should be thinking up and down sinusoid. And this really is like the classic ocean wave idea. Wave up, wave down as it travels. All right. So now we want to talk about interference, which for us is when two or more waves add together. We're going to limit our discussion right now to just two waves, but here we go. So I have now one wave source creating peaks and troughs. I've decided to color the whole thing blue. And I'm going to add a second wave source, which is now colored red. So when you first look at this, you're not sure probably what to think at all. What do I notice? What do I see? I really encourage you to pause the video for a minute. Look at this pattern. See what you see. I talked to some of my students today during our class time. I asked some of them to do this. They took a moment. They thought about what they saw. They spotted patterns, and then when I pointed them out, they felt really good because they knew what they were seeing. So I really encourage you, pause the video for a moment and note what you see. All right, thank you for doing that. So the first thing I want to point out is, here's a place where a peak and a peak meet. And here's a place where a trough and a trough meet. And then if we look, we're like, oh, peak, peak, trough, trough, peak, peak, trough, trough, peak, peak, trough, trough. And you see this sort of pattern emerging. And if I want to think about this as sort of a traveling wave, that is, the waves are traveling in these directions radially outwards, at some point they're going to reach a screen. And so if I were looking at this screen, I would see that all the way along this line, everything is a peak and a peak, or a trough and a trough. This is that first case of superposition that I had done before. This is what I call constructive interference. So these two waves are giving me really tall peaks and really deep troughs. And if we were sitting right here observing, we would see a lot of light. It would be very bright. And so then we say, okay, what else do we see? Well, let's look around some more, and we can find other places where it's like peak and a peak, and a trough and a trough, and peak and a peak, and trough and a trough, over and over and over. And it turns out we can draw a line through those regions as well. And those would also be places on my screen that was very bright. And we can continue this pattern, and over here, similarly, we see peak, peak, trough, trough, right? Peak, peak, trough, trough. And so that's what's happening here. Are we done? Well, no, we're not. There are many places this is happening. Here's a peak and a peak, trough and trough, peak and a peak, right? And so we can now put another line through here. Now, this doesn't show up on this part of the screen, but somewhere over here it would. Okay? And we can keep going, find another one over there. Is that the only kind of pattern we see? Well, no. There is more. What else do we notice? Here we see that we have a peak and a trough meeting, and a peak and a trough, and a peak and a trough, and a peak and a trough. So peak, trough, peak, trough, peak, trough, peak, trough, peak, trough. Right? So not Pikachu, peak, trough. Here, all the way along this line, we have peaks and troughs meeting. That's our other case. That's destructive interference. So now when these two waves add together, you always get 0. All right, let's keep going. Where else does this occur? In this spot here, it's going to be quite dark, right? We're not going to receive very much light at this location because it's completely destructive. And even if you move slightly left or slightly right, well, it's not totally destructive. We saw in the first slide that as they get near this point, it is diminishing the wave. So you do get a patch that's a bit dark. We also see that pattern on the other side. Peak, trough, peak, trough, peak, trough, peak, trough, right? And that peak trough creates another dark region. And we can keep looking to find more of these, and sure enough, we do. We find more peak trough regions that lead to dark spots. Peak trough, right, all the way along here. Peak trough all the way along here. And we notice this alternating pattern of bright, dark, bright, dark, bright, dark all the way along the way. So think about this for a minute. Imagine you're sitting in a completely pitch black room. And in that completely pitch black room, I poke a hole in the wall. And when I do that, you now see light. You're like, oh, look, I see light. We'll say you're sitting, say, right here. Now, you're like, hey, it's too dark. Make it bright. So I poke a second hole in the wall. I now poke a hole here. Well, what do you see if you're sitting right here? Now the room is dark again. Right? So think about this. I poke one hole, you can see. I poke a second hole to let more light in, now you can't see anymore. That should really kind of bother you, right? That's really saying like something's different here. And this is just wave interference. This is saying that there's no light traveling along this path. So what do you do if you want to see? You move your head left or you move your head right. And now you can see again. Lux system. All right. So what does this mean? What is the take-home message here? How do we understand this? Well, if we say like, okay, it's bright, but how bright is it? It's dark, but how dark is it? Well, if we sort of zoom out and look at this, we can see what we call an intensity pattern. This is a place where the center is getting more light. Not a ton more light, but it is getting more light. It's brighter. So the center peak is very bright. Here is also very bright. This is a histogram. How much light am I getting? Right? So I'm getting a lot of light here and then no light, and then a lot of light here and then no light. And so we get these very bright peaks, and then very dark regions in the middle. But is this real? Is this what actually happens? Well, yeah, of course. We wouldn't do this otherwise, right? This is what's called a double slit interference pattern. And if we were in person, we would be able to do this with you. We would give you a laser pointer, and we would give you a little piece of cardboard with 2 holes in it, and you would shine the laser pointer through it. And on the wall, you would get this pattern appearing. You would see these very bright points, dark points. Bright points, dark points, alternating spots all the way along. So this really is, if you're sitting right here, you don't see anything. If you're sitting right here, you see something. So this is proving to us that light indeed behaves like a wave, which is good. Next week, we're going to see that light doesn't always behave like a wave, but at least right now we know that it does. All right. What's the rest of the story here? Well, we're going to call it maximum constructive interference when the 2 waves arrive in a way so that they perfectly add up, right? So here are the 2 waves, and they're going to perfectly add up, okay? We're going to call it perfectly destructive interference when the 2 waves arrive oppositely phased and they destroy each other. And now we have to relate this to what we call path length difference. So where does that come from? Well, what we're really asking is what path did the first source of light take and the second source of light take, and why did they end up being destructive? And we're going to look at, that's what really the goal of this exercise is all about. There's a couple conditions we want to keep in mind. The first is that we want the sources of light to be in phase, meaning we want them both to be emitting light at the same time in the same way. We want the sources of light to be polarized. What does this mean? It means that we want their electric fields both going up and down. If one of their electric fields is going up and down, but the other electric field is going in and out, those can't add up to nothing. And then we would prefer to have monochromatic light, meaning only red or only blue or only green. Because what happens is if you don't have just monochromatic light, what you end up getting is this weird rainbow effect. You get light and dark regions appearing of different colors. And you'll have an opportunity next week during 10th week to kind of understand how these colors add up and why they add up to be white light here or there. All right. So, understanding path length difference. We're thinking about now a sinusoidal shape traveling along from one slit out here to my screen. And we're thinking of another sinusoidal wave traveling along here out to the screen, which of course the wavelength should be equal. And what we're saying is that this wave that went around point R1 traveled a little bit farther than R2. And that's what set up its path length difference, right? So this starts here, and this one starts here. Then we see that from this point on, they're the same wave. But now when this one's a peak, this one's a trough. So at this point right here, we would have no light. And that's what we're after. Now we have highly exaggerated this entire situation. What do I mean by that? Well, this distance here between the holes is really small generally if they're sources. So it really should look something more like the following, right? And you look at that, and if we sort of zoom in there and look, this is really what we're saying. The path length difference over this roughly parallel shape here will lead to constructive interference as such. All right, that's the end of what I had here for you today. I hope this is helpful. Have a great rest of your day. Remember that your homework that was normally due Wednesday is instead due on Thursday because of Doggle. This work on interference will be due on Friday. If you have questions, please contact us on Teams. Please reach out with anything else that you need. Have a great rest of your term. You're almost there. You can do it. Hang in there. Thank you.